Hello and good afternoon. My name is Olaf Kramer from Tübingen University, where I'm a professor of rhetoric and knowledge communication. And I'm very honored today to present the HLF poster flash to you. And the rules are very simple. Our young researchers get 2 slides and get 2 minutes to share their idea. And it's really good and wonderful that we are back on stage and really can talk to each other, because science in the end is all about communication, about interaction, about exchanging ideas. And so we wanted to give our young researchers the opportunity to share their ideas in these 2 minutes talks, and then you can visit them at their poster, because there's also a poster fair if you want to know more. And now you should give a really big hand to the first young researcher who is entering the stage, Lotte Vedage. Lotte is coming to us from the University of Twente. And how does it feel to be the first one?
Well, exciting, yes.
Okay, so good luck and 2 minutes for Lotte.
Yes, so welcome. My talk is about beam-align, which is a new heuristic algorithm that we devised for user association with millimeter wave networks with multi-connectivity. So I guess every one of you uses a mobile phone. I guess every one of you has mobile internet, and maybe some of you already have 5G internet. And with this 5G internet, there are some new technologies, such as multi-connectivity, but also beamforming. And this sounds very good, but there are also some pitfalls in that, since it might not always be best to always connect to the closest base station for your internet. Therefore, we looked into the user association problem, and we made an optimization problem for that. So we wanted to maximize the total data rate between base station I and user J, given that that user can be connected to that base station, and we then have a penalty for all users that cannot be connected. We solved this optimization problem. It's quite hard. And then we tried to find a heuristic solution to that. Since we want to have an easy, as we know from this morning, it's always nice to have a simple algorithm that can, well, perform quite near optimal. And that's what you can see on the upper right corner. Our beam-align, our local heuristic algorithm, decides whether a user should connect to a base station based on whether he is in the beam or not. And if you're in the beam, that means if you're in that blue figure, then you will get good internet, a good data rate. If you're out of the beam, you would not connect with that base station. We then compared our solution to the optimal one, and as you can see in the plot, our beam-align is very close to optimal based on capacity. Thank you.
Thank you very much, Lotte, for preparing the floor for everyone. And now we will go on with someone who comes from the Indian Institute of Science, Shruti Gorantla.
Hi everyone, I'm going to talk about fairness in ranking. So given a set of items, each with a corresponding merit score, if we sort the items in the decreasing order of their score, we get a ranking of these items. However, these items could sometimes be people, for example, candidates applying for a loan. In this case, their educational background and work experience could determine their score. So these scores might be biased sometimes due to human or historical biases, which could cause low representation of some of the groups of people that we are ranking. For example, on the ranking on the left, there are no female candidates in the ranks 2 to 4. But we can rectify this by re-ranking. For example, the ranking in the middle has at least one female candidate in every 3 consecutive ranks. To achieve this, observe that we have moved Bob, who was at rank 4, to rank 6. We call this quantity 6 divided by 4, underranking caused for Bob. Our goal was to study what is the worst case underranking of an individual for group fair rankings. We pose a similar problem for a weaker notion of group fairness, where we want sufficient representation of all the groups in only blocks of ranks, as shown in the third ranking. Here, Bob's underranking is only 5 by 4, which is better than 6 by 4. We gave a fast two-step algorithm to achieve almost optimal underranking for group fair rankings. And in the second case, where we only want group fairness in blocks, we get optimal results. For more details about the algorithms and technical guarantees, please do visit my poster. Thank you.
Thank you, Sruti. Good job. And now we will go on with Kawang Ngoa from the Chalmers University of Technology. The floor is yours.
Hi, everyone. I bet you all heard about the Internet of Things. But what is it about it from a communication perspective? Well, in wireless communications, one of the most important scenarios is multiple access, where you have multiple devices connected to the same base station on the same channel. One of the most challenge in multiple access is that those devices interfere each other. And the traditional solution to that has been to have coordinated and orthogonal access. So the communication resource is divided orthogonally in either the frequency domain, the time domain, the code domain, or both time and frequency domain. And the base station tells the devices when, where, and how to transmit. And that's why this is coordinated. This has been working quite well for the previous generation of wireless networks, but it doesn't work well for the new challenge of the Internet of Things. Because in the Internet of Things, we have to deal with massive uncoordinated access, where we have a large number of low-cost devices, which can be sensors deployed in the environment. These devices are battery limited, so they want to transmit at a low power. Their activity is sporadic and random, so at a certain time, there is only a random and unknown subset of the devices that have something to send. And they send short packets. So it is actually much more difficult to serve 1 million users at a low rate rather than to serve 10 users at a high rate. And that's why we need new information theoretic benchmark to fully understand the challenge and provide guidelines for system design. And in my poster, I will present such a benchmark. Please come.
And now we will move on with Anu Jakar, who comes from the Indian Institute of Technology from Bhilai.
Yeah, thank you. So one of the fundamental question is that suppose if you have a polynomial, then what can we say about the irreducibility of that polynomial or a field? And if it is reducible, then what can we say about the coefficients or degrees of irreducible factors? And in algebraic number theory, computation of discriminant and integral basis is also an important problem. So Newton polygon is an important tool in these directions. So first, what is Newton polygon? So suppose if you have a polynomial fx having integer coefficients, and Newton polygon is always with respect to some prime p. And suppose the highest power of p which divides these coefficients is given by ri. So for making Newton polygon, we just associate a point corresponding to each coefficient ai x to the power I and minus I comma ri. And we form a set which is given by here p that consists of these points I comma r and minus I for each non-zero coefficient a and minus I. And the p Newton polygon is nothing but this is the polygonal path formed by the lower edges along the convex hull of the points when we will see from left to right. So since this is lower convex hull, so slopes with r will be increasing when we see from left to right. So we can see here in the diagram that suppose a polynomial has these coefficients a0, a1, a2, a3, a5, a6, then Newton polygon will be like this. So regarding the application part, in algebraic number theory, suppose if we have an algebraic number field k equal to q theta and ak denote ring of algebraic integers, then we have computed explicit, discriminant and integral basis for Kumar extensions and number fields defined by trinomials. And we can also compute explicit splitting of a prime into prime ideals, product of prime ideals in AK. And suppose if you have polynomial, then we can also compute sometimes Galois group of fx. So to more details, please visit my poster. Thank you.
Until now, we listened to people who had to take a long travel to get here. The next one is a little closer from the University of Bayreuth. Victoria Paneva, please enter the floor.
So what do the displays of the future look like? How do we go from the displays of today, which show a 2D image behind a glass screen, to 3D displays, which show volumetric content in real physical space? So one way to do this would be using acoustic levitation. So acoustic levitation displays use focused ultrasound to trap small particles in mid-air. The device usually consists of one or multiple arrays of transducers, which allows us to steer the particle in any direction. However, the challenge now is what inputs should we give to this system in order for the particle to traverse the path of the intended graphics. So in my poster, I will present an automated pipeline which takes as an input a reference path which consists only of the positions of where the particle should be. Then it takes into account the possibilities of the device, its trapped particle dynamics of the system, and it combines it with a path-following approach in order to compute nearly time-optimal and physically feasible trap trajectories, which contain both trap positions and timing. And finally, the resulting particle motion is executed on the actual device. This allowed us to render bigger and more complex shapes for acoustic levitation displays than it was previously possible. So for more details, come to the poster session. Thank you.
Thank you. And our next presenter is coming from Yale University, and it's quite a title: Quantum Cognition and Computer Systems. Rakwa Paradigma Potokuchi, welcome to the stage.
Understanding and replicating the brain's intelligence is a grand challenge in many fields, and models of cognition are important tools for those efforts. However, cognitive modeling is compute-intensive. A cognitive model describes how inputs like stimuli are acted upon by neural and mental mechanisms to produce outputs like decisions. These models contain complex features like nonlinear dynamics, optimization, and more recently, researchers have begun using quantum probability in addition to classical probability to model decision-making. Given these complex models and the recent emergence of practical quantum computers, my research asks how we can use existing quantum computers to accelerate cognitive modeling. I begin by taking a group of representative cognitive models and explore various quantum implementations for them. Our preliminary implementations agree very well with classical simulations. However, we find that the accuracy of the results and the processing time depend significantly on the specific choices among seemingly equivalent alternatives. This opens up many research opportunities at various levels of the computing stack. This work is significant because it's the first demonstrator of the mapping of cognitive models to quantum computers. It also presents a new benchmark suite to guide the design of quantum computers. This is important because the existing quantum computing stack is heavily influenced by problems from a few domains like physics and chemistry. To benefit broader scientific communities, it is important to use diverse applications, and our work is an important step in that direction. And my poster has more details about the specific models and their quantum implementations. And I hope to see you there. Thank you.
And now we will continue with Denise Zarikaya from the Vrije Universiteit Brussels. Welcome.
Hello. Which norms do govern science? I mean, we want to be objective. At times we want to be rational, maybe even kind of cold, but I mean, ethics is everywhere. When we decide what to work on, when we decide how to tweak the likelihood of a type 2 and a type 1 error, or when we press a complex thing into a 2-minute presentation. And I want to focus on this last question in the context of science advice in this joint work with Simon Blessenol. And we looked at the literatures which norms are discussed for science advice. And in Germany, we have a huge tradition of saying, well, just make uncertainty explicit. But the empirical data show that people just don't update their beliefs when they don't understand the statement. So another tradition in the Anglo-Saxon area is just say whatever yields to good policy outcomes when you advise a decision maker. But we argue that this is procedurally unjust, because we scientists, we should not have this ethical mandate to decide what's good or bad societal outcome. So we propose another norm for science advice, which says you should inform. Say something that make the credences of the addressee accurate. So we push in that paper forward that you should learn about framing and how to communicate your research when you engage in science advice. So you can see the details in the paper or at the poster, and feel free to discuss with me just in general whether science can be objective, whether it should be objective.
Denise, this is a poster that I will definitely visit because it's really going into my field of science communication. Thank you very much for that. Now, we move to France, to the Université Paris Sciences et Lettres, and we will listen to Quia Quoc Bois Tram. Go ahead.
So, xin chào. That's how I say hello in my language. So I'm going to talk to you very briefly about my PhD topic, which is on control theory, so the control of dynamical systems. So in order to understand this, you need to understand the two concepts that are hybrid systems and observers. So what are hybrid systems or hybrid dynamical systems? They are the dynamical systems that can be described by these sorts of equations where the vector x, or we call the state, containing the physical variables such as velocities, positions, currents, voltages, and so on, can evolve in both a continuous and a discrete or discontinuous way depending on its value. You also have U, the input, that may either control the system or disturb it, and Y is the measurement, something we get from the system. Now you may wonder which kind of system can be modeled as hybrid systems. Here are some examples of them. They range from robots, the walking ones, to biological systems such as neurons in your brains, or a bunch of fireflies interacting and flashing. If you look at the system, the only thing you know is this output and not the state inside. So there is a need to estimate the system state for various purposes, like control or parameter estimation. So in order to do that, we rely on these algorithms called the observers. So the virtual system that from the system's input and output estimates its state. So my work is basically about how to design observers for the hybrid systems. I've summed up my latest result in my poster. You will find it very easily. It's the purple one. And if you like control theory, don't hesitate to come and discuss. Thank you.
Just to mention it, by the way, no one took longer than 2 minutes until now. Really great job. And our next speaker is Jorge Wagner from the Federal University of Rio Grande do Sul. You're welcome.
Hello everyone, good afternoon. So, designing and evaluating immersive analytics environments. What is immersive analytics? I think a good way of introducing it is that we are trying to leverage advancements in virtual reality and augmented reality to bring us closer to that vision that we got from science fiction movies of humans interacting with data around them and discussing it with other people. And maybe more importantly than that, thinking about how and when would that be helpful to us, besides being pretty cool, I hope. So in my PhD thesis, we hypothesized that this kind of environment could be very useful, for example, for the exploration of spatial temporal data. So we borrowed this space-time cube visualization concept from the geo-visualization community, and we implemented it in VR. The space-time cube kind of extracts movement trajectories from a 2D map into three-dimensional space using the vertical dimension as a time axis. So here you can see some pictures of myself interacting with data in this immersive space. I can stretch time, compress time, inspect different positions, and so on. So my goal of this work is to introduce new guidelines to this field that has been growing a lot over the last 5 years. And to that end, I'm doing user studies and investigating how people perform in these environments. We have compared how people performed in this immersive environment to a standard desktop one. We have explored different perspectives like exocentric or egocentric or large-scale, small-scale environments, and also different forms of interaction like virtual hands, pointers, and so on. And right now, I have to finish my PhD by investigating how this kind of environment will perform with larger scale data sets from the real world. So I hope to see you soon downstairs. Thank you.
Thank you. So many interesting projects we can present here. And we will now continue with Thomas Burns from the Okinawa Institute of Science and Technology Graduate University. The floor is yours.
Hi. So in deep learning, we typically use a lot of vector spaces and linear algebra. And don't get me wrong, those are great tools. But today I want to tell you about how we can use geometry and topology to better understand a prototypical AI environment, a grid world. Grid worlds are these flat 2D environments of squares glued together on their sides, and they have labels. In this case, I've labeled the agent as a koala, the movable object as a beach ball, and you have some empty squares as well. Each vertex in this graph is a state, a labeling of the grid world, and you can see them connected by edges according to generators, which are colored, the push-pull generator, the move generator. And those are local relabelings of the grid world. And you get this nice staircase structure, which is pretty cool. What's interesting is if you add, of course, one extra square at the end of this corridor on the right, then the staircase will extend up by one step. Here's a more interesting example, a 3x3 grid world. And in this case, there are two scales of geometry that you'll notice. Now first, just to point out, the labelings I'm drawing on the right and the shaded vertex is the state we're in inside this object called a cube complex. And what's cool about these two scales of geometry is that you see these larger clumps of clusters of states. Those are where the object is static. And then if you zoom into one of those clusters, the remaining states are where the agent can freely move around in the empty space. What's also interesting is if you add in some cubes, we add in n cubes for commuting moves, then you can actually find that there are features of this complex, in particular curvature, which detects potential collisions. Come to my poster to find out more about that. And in general, this opens up a new way of studying AI problems, not just using vector spaces or linear algebra, but indeed much more interesting, to me at least, mathematics. Thank you.
Thank you very much. Many eyes today are looking at London. And now we've got someone from Queen Mary University's Luis Judowitz. You're welcome.
Well, one of the main problems in geometry is being able to classify all the different shapes and spaces you're working with. But the main question is, how exactly can we do this? So you might come up with an idea that just like you can decompose natural numbers into products of prime numbers, you might decompose your manifolds into prime manifolds and build things up that way. And over the past few decades, it turns out that using diffusion heat type equations to do this is quite fruitful. So one example is the Ricci flow equation that I put up there in red. Now what Ricci flow does is it tries to average out the curvature of the manifold by shrinking shrinking parts of positive curvature and expanding parts of negative curvature. And you can see an example of that in the picture I put up on the left. Now one issue with this is that the small cylindrical regions in the picture, they have very positive curvature, so they could pinch off quite quickly and cause singularities. In order to bypass this, you could do what's called Ricci flow with surgery, where you cut through the cylindrical regions, cap off the areas, and try and continue the flow in two components. Now we can do this in dimensions 2 and 3 because we know that at very small scales, the singularities look like cylinders. But in higher dimensions, there are issues, and one of the main ones is the singularity models can have singularities themselves. So an example I've put up in the upper left corner, you can see what your singularity model might look like very close to the singular time. But as you get right to the singularity model could have a cone point, which is another form of singularity. So in my work, the main idea to bypass this and to recover some topology you can lose, if you can see in the picture, is to just zoom in around the cone points again and again until you reach a fine enough resolution that no more singularities form. Now you can arrange this in a tree structure, like I put in the lower right, and you can use this to prove various things, but my main result was a local finiteness theorem for shrinking singularity models. This really speaks in favor of classification, and it's a good step forward, but there's still a lot of more work to be done, and I'd really welcome any discussion during the poster session. Thank you.
Thank you very much, Louis, and we will continue with Christian Boddy from the University of Free State.
Now, we have a long theoretical title. With just 2 minutes, I will just explain roughly the idea of bicontinuous semigroups. Now think of your favorite PDE describing a dynamical system. What are you doing? You look at this PDE, rewrite it as an initial value problem on an infinite dimensional space, say a Banach space, and the solution of this initial Banach space problem are given by operator semigroups. Now, but not all operator semigroups are strongly continuous with respect to the underlying Banach space structure. So the idea is to equip the Banach space with another additional locally convex topology with some additional requirements. For example, the space of bounded continuous functions equipped with the supremum norm. This is a Banach space. Equip it with a compact open topology. Or if you have the space of bounded linear operators, take the strong operator topology. Now on these spaces, you have also, because they are Banach spaces, operator semigroups. For example, the translation semigroup. Now this is on the space of bounded continuous functions. It's not strongly continuous with respect to the supremum norm, but strongly continuous with respect to the compact open topology. Now there are several other examples like the implemented semigroups, and this occurs naturally in quantum physics, for example. So if you want to discuss the more theoretical framework of bicontinuous semigroups, extrapolation spaces, and maybe a little bit of perturbation theory, come to my poster, and I'm really glad to discuss with you all your questions. So vielen lieben Dank.
Okay. Thank you. As you see, our next speaker will be Alejandro Tolcachier from the Universidad Nacional de Colombia. No, Córdoba. Sorry.
Hi, everyone. We are interested in studying geometric properties of differentiable manifolds. For instance, what is the shortest distance between 2 points in the manifold? What is the curvature of the manifold? Well, apart from the plane and the sphere, the geometry can be very complicated, but also rich. well, a nice universe to work with are Lie groups, objects which combine the differentiable structure with the group structure in a compatible way. And from Lie groups, we can construct compact examples, manifolds, called solved manifolds and nil manifolds, which are obtained by quotienting your Lie group by a lattice. And my research is related to classifying flat submanifolds using tools like Mostow's theorem, which mainly says, but not in the slide, that if the lattices are isomorphic, then the solved manifolds are diffeomorphic. That is, the geometer's eyes cannot distinguish between these two, even with glasses. And here is when algebra enters the stage. Essentially, a flat Lie group has the structure of a semi-direct product, and one can obtain those lattices compatible with this structure, called splittable lattices. There is an action of a finite abelian subgroup, H, of GL and Z, such that if two of these subgroups are conjugated, then the lattices are isomorphic, and therefore the solved manifolds are diffeomorphic. So this allows us to classify splittable flat submanifolds in terms of the classification of finite subgroups of GL. I would be delighted to tell you more details in the poster session. Thank you.
Thank you. And now Carla Rizzo will take over the lectern from the University of Coimbra. This time it's right.
So, as all you know, unfortunately, the world is not completely, in general, commutative. Even if at school they, in general, teach us just commutative mathematics, this letting us thinking like the word, this is the only language for the world, this is not true. I know, it's quite disappointing, but what we can do. So, in algebra, in non-commutative algebra, okay. A really nice question is, how big is the center of an algebra? That means, how far to be commutative is an algebra? To answer this question, it's quite interesting to introduce polynomial, a non-commutative variable, and try to understand when this kind of object commutes in some way. This kind of polynomial are called central polynomial. An example in M2, in the algebra of matrices of order 2, is the polynomial, the identity that you can see in there, in the middle of the screen. And this identity tells us that the polynomial underlying is a central polynomial for the matrix. So what does it mean? That this polynomial, when we evaluate this polynomial in elements of our algebra, this is, we obtain a matrix that commutes with any other matrix. So our question now becomes, how many central polynomials exist? And to answer this question, we define growth function that allow us to have a quantitative answer to this question, or at least we try to estimate this in some way. But now, I want to challenge you more and ask, and what if we consider it not just an algebra, but an algebra with involution? If you want to know the answer, please join me to my poster.
Thank you. Now we are already entering the second half of our HLF poster flash, and we will do this with Carlos Tamayo from the National Autonomous University of Mexico. Welcome.
Hello, everyone. You are a lot, the people. Okay. Clifford analysis is a natural generalization of complex analysis to higher dimensions. In this context is stated the Young problem. Given a surface fractal in general and a data function f, we need to find a function phi monogenic oxide of S that satisfies the Fourier equation in black. There are existing conditions of solvability for this problem involving the Minkowski dimension of the surface S when the function f is in a Holder class with exponent no. Using the recently defined Marcinkiewicz exponent, we were able to prove new solvability conditions for this problem involving the dimension of the space and Marcinkiewicz exponent. However, the question is, how does this new condition improve the existing condition? Well, the second equation in black shows us that this new condition is better, or at least the same that the old conditions. Also, we were able to prove in the third equation that in dimension 3, there exists an uncountable class of surface S alpha beta, where this inequality is exact. We proved that through the construction of the surfaces S alpha beta. We can see an example of these surfaces for specific values of beta and alpha in the right corner at the bottom. Thank you. I hope see you in the poster session.
Thank you, and time for our next speaker, which comes from the Indian Institute of Technology or Indian Institute of Science, Rishikesh Kayala.
Hello everyone. Today I'll be presenting a combinatorial problem from quantum physics. So quantum entanglement says that two particles can be very far away and the wave functions can still be dependent on each other. ZZ states are a certain type of entangled states which involve more than two particles. These states were studied out of fundamental curiosity, and they also have several applications in quantum communication and quantum cryptography. So to create these ZZ states, physicists use something called quantum photonic experiments, but most of these experiments were leading to low-dimensional ZZ states. And it turns out that the main problem to create higher dimensional ZZ state is because of a graph theoretic problem. Each quantum photonic experiment translates to an edge-weighted and edge-colored graph, that is A translates to B, and A translates to B, and the dimension of the ZZ state of the experiment in A corresponds to the number of colors in B. And to create a ZZ state from an experiment, this graph should have a particular property called being perfectly monochromatic, and then you'll be able to create a ZZ state in the corresponding experiment. So now the problem reduces to color the graph with lots of colors and maintain a particular property called perfectly monochromatic. Then you'll be able to create a high dimensional ZZ state. What we proved was that there is a large class of graphs. However you color them, you can't create high dimensional ZZ states with them. And to know the exact definition of the problem, you can visit my poster. Thank you.
Right now, we hear about the Ukraine quite a lot, and I'm really happy that Olena Atlasyuk from the Ukraine is here, from the National Academy of Science of Ukraine, to talk about her scientific work.
Hello, it's my great pleasure to be here with you. And today I will show you two of my main results concerning character of solvability and continuity in a parameter of solutions of the most general inhomogeneous boundary value problems. So, first of all, what will happen with the index of the operator in case of overdetermined and underdetermined problem if you don't know the exact analytic representation of this operator? And the second one, concerning continuity in the parameter. So, the necessary and sufficiently conditions that guarantee the continuity in the parameter are the existence of the invertible operator and the existence of the strong convergence of set of these operators. As you know, in general case, it's not true, but for us, it holds. So I kindly ask you to visit my poster, and the last one, please stay with Ukraine. Thanks a lot.
Thank you very much, Olena, and all the best to you. Now we move to Ghent University and Vichev Kumar, who will now enter the floor.
Mathematical inequalities play a very important role in mathematics as well as in engineering and other branches of sciences. So in particular, I'm interested in how mathematical inequality can be used to prove certain theorems in Fourier analysis and harmonic analysis. So let me define what is Fourier multiplier first. So a Fourier multiplier is an operator which I denote by Tm associated with the symbol m, such that on a certain function spaces where Fourier transform act well, such that this following identity which you see hold. In particular, it says that when you apply Fourier transform on an image of a function, then it gives a multiplication by the Fourier transform of that function evaluated at certain point, and that justifies the name Fourier multiplier because it's multiplied by a number. Okay? And a central question is harmonic analysis is to find condition on symbol of Fourier multiplier so that the corresponding Fourier multiplier is bounded on certain function spaces. In 1960, Lars Hormander investigated this question on Lebesgue spaces and found sufficient conditions, and these theorems are now known as Hormander multiplier theorem. And the main tool he used some classical inequality involving Fourier transform known as Paley inequality and host of Young-Paley inequalities. So recently, two-parameter deformation of Fourier representation inspired by Fourier representation was proposed, which is known as generalized Fourier transform, and we are interested to explore Hormander multiplier theorem in this more generalized setting. So if you want to know more about this setting, so please come to my poster. Thanks.
Once again, we are in Germany, in one of the other traditional German university towns, Göttingen University. Giselle Matta-Mariaga, you're welcome.
Hello. So Fourier integral operators are an important tool in the analysis of differential equation, and understanding the principal symbol is also highly important. The core of the theory is an oscillatory integral like the one on the screen, and the exponent, the phase function phi, is usually assumed to be real valued with no critical points. However, we can also do this with a complex value phase function. And in the words of Treve, one needs to be willing to deal with Lagrangian manifolds that are neither manifolds nor Lagrangian. How do we do it? By using almost analytic extensions. Now, he was referring to the work of Mellin and Sjöstrand in 1975, where they defined complex versions of the geometrical objects. Their Lagrangian manifolds are in reality an equivalent class, and they define a line bundle that is more actually like a sheaf. With these two things, they were able to provide a principal symbol map, but this was done very abstractly. So my work was a little bit of translation. And now I can provide explicit formula for the principal symbol. And the next step is to use it to actually study hyperbolic problems. I'm particularly interested in surface waves, or like Rayleigh waves, sometimes are referred to. They appear in several real-life situations, like, for example, when we model earthquakes, and that's where this picture over there comes from. They have been studied from the point of applied mathematics. Now I'm hoping to provide a more formal approach to their studies with the help of this Fourier integral operators with complex phase. Thank you for your attention.
Thank you very much. In a way, a poster flash is a test for the flexibility of your mind as you have to move from one topic to the other, from one discipline to the other. Now we will make it a little easier for you as we've got a cluster of presentations that deal with COVID-19 in one way or the other. And this cluster starts with Tolulope Adebucho from the Federal University of Technology in Akio. Welcome.
Hello, everyone. The alarming rate at which COVID-19 virus spread across the world and its huge impact cannot be overstressed. It caused a lot of deaths, and many people were hospitalized. And due to this, containment strategies were put in place, such as wearing a face mask, hand washing, maintaining social distance, and the likes. However, this virus continues to evolve into different variants. And in countries such as Nigeria, where there are limited human resources and hospital facilities, it becomes a problem to properly manage cases, COVID-19 cases. So this research, I'm proposing a framework that will help to curb the spread of the virus in the country. This framework consists of 3 modules. The first module, which is in the top left corner, will deal with acquisition of data from the patients. And this will be stored on the cloud for pre-processing and analysis. This analysis will help the health physician to detect and monitor the health status of patients, especially patients with mild symptoms that do not really need hospitalization. And from there, the results will be transferred to the patient for feedback. I invite all of you to my poster for your contributions and comments. Thank you.
Thank you very much, and we will go on with another presentation that deals with epidemics. It's Baltasar Espinosa from the University of Virginia.
Hello, everyone. Epidemics can be seen as complex adaptive systems that are modulated by processes that occur at multiple scales. Individuals' behavioral choices modulate as the epidemic progresses, as the risk of infection changes. In this regard, my research work deals with mathematical models that explicitly track the epidemic progression over the population scale, but also modulates the behavioral response that accompanies with this other process. In this figure, you can see the schematic representation in the top layer of the components that modulates behavioral responses, and in the bottom layer, the epidemic over these agents. Some of the results that we have obtained with this framework is that behavioral response, as you can see in the left figure, do well on reducing the number of active cases. However, this may increase the final epidemic size. Also, economic and social disparities may create social heterogeneities, and this will increase also the impact of behavioral responses. Finally, we can see in the right figure that, in contrast with the classic theory, behavioral response will increase the final epidemic size on different factors. To find more details about this work, please stop by the poster.
COVID-19 affected the whole world, but also inspired research everywhere. And now we move to Africa, to the University of Rwanda, where Hetzron Legrace Ndyao A.M is coming to us.
Hi, everyone. We are going to talk about imperfect vaccine. Most of the vaccines that have been made since yet are imperfect, and because they do not provide full protection. And people doesn't want to be vaccinated because of the side effect of the vaccine. And still, government use vaccination to control infectious disease and other strategies like lockdown, like what happened in Covid-19 to reduce the movement of individuals in the community. In my work, we are going to use mathematical model where we consider an vaccinated individual and unvaccinated individual to study the interplay between different types of imperfect vaccine and the level of population turnover. We found that in the community with a strong turnover, we can use an imperfect vaccine designed to reduce the transmission to control the disease in the community. But when the turnover becomes weak, we need a more efficient imperfect vaccine designed to reduce the transmission and a mass vaccination campaign. And we recommend a vaccine design made by the converse trade-off between the ability to reduce the transmission and favoring the recovery. If you want to know more about my work, I invite you on the poster session. Thank you.
Thank you. And now please welcome Alexander Rodriguez from the Georgia Institute of Technology.
Hello, I will talk about AI for epidemic forecasting. I might not need to explain you why epidemic forecasting is important, but you may be wondering why AI. And our motivation is that because we have an increasing data collection. For example, we have data set from Google, like search trends, or from Facebook, which have symptomatic surveys. And these data sets are usually more sensitive to what's happening on the ground, more specific, and also more timely than other data sets in public health. However, traditional methods based on differential equations or AM-based modeling, they have difficulties incorporating these data sets. So we can use AI, data-driven specificity of AI, in order to incorporate the data sets, but however, there are some challenges. For example, AI doesn't have an understanding of disease spread dynamics. The data is sparse and limited, and there are multiple data quality issues. For this, we have created several frameworks to approach these problems, and this is an example of our frameworks in which we are trying to bridge AI and epidemiological models. In this framework, we can see number one, which have the data sets enter into a neural network that is going to predict parameters of the simulation. This simulation is a million-sized population. We are simulating the transmission and the progression of the disease based on principles of epidemiology. And this is a tensor-based operations with fully differentiable framework. We are in number three. We are aggregating the results from the simulation. We compare against the ground truth data, and we have a loss function that which we can use in order to because it's a fully differentiable framework. We can apply backpropagation, gradient descent. This is an example of the frameworks that we have created. I invite you to see more of my work in the poster presentation. Thank you very much.
We will now enter a next topic, a next cluster, a cluster that's dealing with environmental issues, environmental topics. And Letizia Oneyekbu will be the first on the floor from the University of Port Harcourt. Welcome.
Good afternoon, everyone. I'll be talking on improving crop yield using IoT and AI. Globally, there's an increasing rise in food insecurity, especially in Africa. And this is attributed to climate change, weather condition, diseases, pest infestation, and soil infertility. We're proposing to solve this problem using the IoT, Internet of Things, and AI. The IoT system will be installed in the farm to help the farmers to take a prompt action. The AI model will be trained. First of all, I have to train our AI model. That they train it using the data sets that we collect from some of the organizations that we have in Nigeria, because I'm using Nigeria as my case study, but it can also be used in Africa. So this system will help the farmers to know what is actually happening in their farms. Now, of course, we're also going to use the IoT system to detect the parameters in the farm. These parameters will be sent to the AI model that will be deployed to the cloud. Then the farmers will also have an Android phone that will tell them, that will enable them to download what is happening in the farm, to tell them what is actually happening, so that they will take a prompt action. They will know when there's insect infestation in the farm. They also know when to apply the right insecticides. They will also know when to use the right fertilizer. They also have outputs. The expected outputs from what you are seeing on the rightmost part of my slides is that there will be increased crop yield. They will also help the farmers to take prompt action. And what is happening in the farm will also be determined at the site. Then the outcomes is what you are seeing on the leftmost part. The outcome is that it will help the farmers to also know what is happening. It will help them to take care of their farm. And by doing that, by applying the right fertilizers and the right insecticides, it will help the soil. It will improve the soil and also in the environment. For more details about this, my systems, kindly visit my poster stand. Thank you.
Thank you. Now, University of Bath, Oluwatosin Babasola.
Thank you. Cocoa is a major source of exports in Africa, in particular West Africa, where Cote d'Ivoire, Ghana, Cameroon, and Nigeria are top producing countries. In fact, the production in these countries accounts for over 70% of the world cocoa production. However, there has been a decline in the yield of this crop in this region, and climate change is being identified to be one of the significant factors that is influencing this decline. So, what we aim to do is to use mathematics to understand the behavior of these crops, and then to know how climate change actually affects the crops. And in doing this, we consider 3 stages, which is flowering, pod formation, and then when the pod became ripe, then harvesting. So, and we are going to use a mathematical model, a time delay modeling, to understand the behavior of these crops at this time. All right, so we have parameters which are representing the rate, and we have a Fourier function which accounts for the influence of climate variables on the crops. Also, we have the delay parameters, which is represented by a lag, and then this can be identified using a cross correlation between the production and the data considered. For illustration, we use rainfall data, and this helps to identify the delay. The early result shows that the flowering follows a periodic behavior which could be attributed to the rainfall pattern. To know more about my work, I look forward to welcoming you all to my poster session. Thank you so much for your attention. God bless.
Thank you. Next in line is Jorge Arrojo Esquivel from the University of California in Davis. Your 2 minutes.
Thank you very much. In natural ecosystems, sometimes they present alternative stable states, which are states of and different configurations of the population densities that persist over time. For example, in the ecosystem that I work in, which is the temperate rocky reefs in the ocean, we have two alternative stable states. On your left, you're going to see the kelp forest, which is highly productive, and on your right side, you're going to see orchid barrens, which are low productive. And although they can persist over time, in reality, what we observe is that these ecosystems, these different configurations of the ecosystem, they vary over time because of disturbances such as marine heat waves or changes in nutrient concentrations. It is thus pretty interesting and pretty important for us to understand how resistant are these different alternative stable states to these changes due to stochastic disturbances. We can measure that using a metric of the deterministic dynamics of our models that is called quasi-potentials. These quasi-potentials, when we have a model in one dimension, for example, can give us these nice landscape figures where our alternative stable states are cups or valleys. The deeper the cup is, the more resilient our alternative stable state is. If you want to talk a little more about the mathematical details and how we can use this type of metrics in more than one dimension, please come to my poster. Thank you.
Thanks, Jorge. And now we will meet Tracy Ullerich from George Mason University.
Hello, everyone. So today I'm going to talk to you about how I utilize mathematics to help inform drug targeting for cancer treatment. In particular, our goal is to create a dynamical system model for the mitogen-activated protein kinase pathway. A lot of big biology words there, but to break it down, this pathway is very implemented in a lot of cancer research. It regulates gene expression and cellular growth, and dysregulated MAPK signaling has been implicated in a wide range of cancers. In particular, this pathway is interesting because it has a protein within it that mutates, so we're interested in seeing how that mutation could potentially affect the dynamics as well. Furthermore, once we get that dynamical system model, we can go through and check for biological properties. So this is something like adaptation, where if we're looking at applying a drug to the system, seeing where this pathway is adapting to that drug and essentially negating its effect, as well as looking for conservation laws, which can pose some issues when we start talking about different properties, as well as just something to kind of keep in mind for the biologists. So how we exactly get the dynamical system model? Well, we start off with our biological data. So it's very messy, it's very noisy, and we have not a lot of it. I think this is over a 24-hour time period, and we have maybe 8 total times we recorded. So we take this biological data, and we use some novel data-driven techniques, and we infer the dynamics. So we essentially create a dynamical system model, which we can do either one of two things with. We can either go to the completely mathematical side and check for those properties I mentioned, so adaptation, conservation laws, and so on. Or we can take it more to the biologists and give them something they can work with, so we can recreate the biological network structure. So kind of figure out like a protein-protein social network, who likes who doesn't like who, and go from there. So if you want to learn more about the techniques I'm using to infer these dynamics, please stop by my poster. Thank you.
Okay, our next speaker comes from the University of Tanzania. It's Albert Christian Zovonsono.
All right, thank you for the introductions. So for this talk, I'm representing stochastic niche-based model for the evolution of species. So the idea is basically we want to be able to come up with a model, evolutionary model to generate and also describe species-level phylogeny. So at species-level phylogeny, you have two events. So you have speciation events. That's an event where you have a species branches into two completely new species, or you can also have an extinction event. So extinction event is basically a species went extinct. So the idea is that we want these speciation events and also excision events driven by ecological niches. So the first stage of the work is basically we want to describe the evolutions of ecological niches throughout time. So as an illustration, you can have a look on this figure on the left. So basically we have a niche space that is formed by two environmental traits. You can consider the x-axis to be temperature and then y-axis to be like rainfall, and then you have this niche space, and then inside this niche space you have niche appearing over time, and then species can move between this niche, and as species move from one niche to another, that triggers a speciation events in your phylogenetic tree. So we also want to incorporate the idea of niche occupying some geographical locations. So so basically the next thing is that we want to consider niche space that is not only limited by two environmental traits, they can have finitely many environmental traits, and then we consider that all species that share the same fundamental niche, and then we have to model how each parameter evolved throughout time. So we consider some Markov chain and also the influence from other locations. And then the next thing that basically is that we want to connect from going from niche process to speciation process, because at the end of the day we want to be able to come up with a phylogenetic tree. So if you're interested with this topic, please consider visiting me during my poster session. And also just a fun fact before I ending my talk, I find that this year logo is very interesting because if you look up the circular phylogenetic tree, it resembles very close with this year logo with that circular tree. Okay, anyway, that's all from me. Thank you.
Okay. Oops. Thank you very much. And now we've got one presentation left, and we thought we'd talk about one of the secrets of mankind. Air conditioning is either too hot, too cold, too wet, too dry, whatever. Can deep learning change something? A warm welcome from Monash University, Rakshita Godahova.
Hello everyone. So a major portion of building energy is these days consumed by air conditioning systems. So the major reason for this phenomenon is the usage of static thermal set points. So what are static thermal set points? Static thermal set points is maintaining the same comfortable temperature levels inside a building irrespective of its occupancy. So this strategy is very beneficial when the building rooms are occupied, but maintaining the same comfortable temperature level during the building unoccupied periods can cause massive energy wastage and therewith increases energy-related expenses. My research proposes a solution for this problem by proposing a model that can be used to optimally control the thermal set points of a room, specifically during its unoccupied periods. So the figure in this slide shows my model in a nutshell. So basically it has two parts, forecasting and optimization. The forecasting parts predicts the future inside temperatures of the room, specifically for its unoccupied period, using deep learning technologies. Then, using these predicted temperatures, I optimally control the thermal set points inside the room during the optimization phase. So I applied this model to control the thermal set points inside the university lecture theater and found that my model can lead to 20% of energy savings. So thank you very much. I invite all of you to visit my poster during the next few minutes to learn more about this. Thanks a lot.
Okay, thank you very much. And I think they all did a great job in talking in front of this very special audience, in front of some of the pioneers and heroes of their field. And so I guess we should give them another big hand, our young researchers. And all of them will be very happy if you visit them at their posters. And remember, science is about communication and interaction. Enjoy the HLF and have a good time here in Heidelberg.